Hello everyone, welcome to VYAS Edification Quota. In this session, we are going to discuss all and exercise solutions of class 11 chapter number 11 thermal property of matter. As you know, if we talk about thermal properties of matter, we have matter in the form of solid, liquid and gas. So in this section we will try to understand different property that is exhibited by the matter, that is thermal property. Clear? So now we are going to discuss each and every and exercise question with detailed video solution concentrated on a screen. Now student, we are going to discuss question number 11.1, and actually this question is based on conversion of temperature scale. Actually in this question we will convert temperature that is already given in Kelvin into degree Celsius and degree Fahrenheit. Clear? So now we are going to discuss this question. Concentrate. In this question it is given to you the triple point of neon and carbon dioxide are 24.57 Kelvin and 216.55 Kelvin respectively. Clear? Now we have to express this temperature on the Celsius and Fahrenheit scale. Clear? So dear student, we know one relation, and this relation is what? Temperature in Kelvin. This is given by temperature in degree Celsius plus 273.15. Clear? Exactly we have this one. Clear? So in this question it is given, if we talk about neon, so for neon value of triple point is given. We can say temperature is given in the form of Kelvin, and this temperature is triple point of triple point. Clear? And this temperature is given to you 24.57 Kelvin. Now can we convert this temperature into degree Celsius? Yes, we can utilize this relation. So temperature in degree Celsius, it is given by T in Kelvin minus 273.15. Clear? So from here you can write like this: Kelvin temperature, so 24.57 minus 273.15. Clear? So from here we can see this is 15 minus 7 we have 8. Clear? This is what? 0. So we can say this is 5. Clear? This is 0, this is 5. Now from here we can see this is what? 2. This is equal to 8. Clear? And we can say this is 6, this is 4, and this one is 2, and here this is minus. Clear? So we can say this is answer in degree Celsius. Clear to everyone? Clear? Now can we convert this temperature into we can say Fahrenheit scale? Yes. So how can we convert it into? So from here you can say, let's suppose if I am taking references, so from here you can say, let's suppose this is 0 degree Celsius, this is lower temperature scale, and upper temperature scale we have 100 degrees Celsius. Clear? In an external condition, that is 1 atmospheric pressure. Clear? Now if we are talking about Fahrenheit scale, from here we can say lower limit we have 32 degree Fahrenheit, and this is what? 212 degree Fahrenheit. Clear? So if you find relation between Celsius scale and Fahrenheit scale, it is given by, listen carefully, let's suppose this is C, this is F. Clear? Or you can say this is TC and this is what? TF. Clear? Now we can write like this: TC minus 0 divided by 100 minus 0. This should be equal to TF minus 32 divided by 212 minus 32. Clear? So from here we can write like this: this is TC by 100. This should be equal to TF minus 32 divided by 180. Clear? From here we can say this and this is cancelled out. Clear? So we can say TC divided by, now listen carefully, if we cancel with 2, this is equal to 5, and TF minus 32 divided by 9. Clear? So from here we can say TF minus 32, this is given by 9 by 5 times of TC. Clear? So value of temperature in Fahrenheit, this is given by 9 by 5 times of TC plus 32. Clear? So this is relation. Now we can place value of TC here and we can find value in Fahrenheit. Clear? So from here we can write like this. I am again writing this relation here. Value of temperature in Fahrenheit, this is given by 9 by 5 times of TC. Clear? 9 by 5 times of TC plus this is equal to 32. Clear? Now from here you can see for neon value of temperature in degrees Celsius, it is given to you minus 248.58. Clear? So minus 248.58 plus this is 32. Clear? So we can see this is equal to 9. If you cancel it, clear, then we can say 5 4 20, 5 9 45, we have 3, 5 7 35, clear, and let's suppose this is 5 1 5 plus this is 32. So if you multiply it with 9, we can write like this, this is 9, we have 3, we have 6, we can say 7, this is 8, so 36 and 8, we can say that is 44, we can say 44, clear, and this is in minus plus 32. So from here we can say, if you write this is 5, this is 1, this is 4 minus 0.39, this is degree Fahrenheit, clear. So like this we can convert this temperature in degrees Celsius into Fahrenheit, clear to everyone. Now in this question it is also given, we have to convert the triple point of carbon dioxide also in degree Celsius and degree Fahrenheit, clear. So now we can say triple point of carbon dioxide we have 216.55 Kelvin, clear. So now if I talk about carbon dioxide TTR, this is given this is minus, no, 216 plus 216 point, clear, 55 Kelvin, clear. So 55 Kelvin. Can we convert into degree Celsius? Yes. So we can write like this, T in degree Celsius, this is given by we know this relation, clear, T in Kelvin minus 273.15. So T in Kelvin minus 273.15, clear. So what is temperature in Kelvin? Temperature in Kelvin is given by 216.55 minus 273.15, clear to everyone. So from here you can say, if we subtract it, we can say this is 0 and we can say this is 6, clear. Now we have 2, so 12 minus 6, again we have 6, this is 6, we can say 5, clear, and this is 0, clear, and we can write this is minus, clear. So from here you can see we are getting this answer minus 56.6 degree Celsius, clear to everyone. Now we can convert this degree Celsius into Kelvin, into degree Fahrenheit also. Yes, actually we know this relation, temperature in Fahrenheit, this is given by 9 by 5 times of Tc plus 32, clear. So 9 by 5 times of Tc, value of Tc is given minus 56.6 plus this is 32, clear. So 9 by 5, and we can say if you you can actually cancel here already. So from here you can say if we cancel this one, this is minus 1 point, we can say 3, so minus 11.3, clear. So if you multiply, we can say this is 27, we have 2 left, so this is what 11, we have 1, this is 10, so minus 101.7 plus this is 32, clear. So from here we can say this is 7 and we can say this is 9, clear. Here we have 9, this is 6, yes or no, and we can say this is degree Fahrenheit, clear. So like this we can convert triple point of neon and carbon dioxide that is already given in Kelvin into degree Celsius as well as in the degree Fahrenheit, clear to everyone. Now student, we are going to discuss question number 11.2, and in this question it is given to you two absolute scale A and B have triple point of water defined to be 200 and Kelvin and we can say 350 Kelvin, clear. So what is relation between temperature TA and TB, clear. So from here you can say, because important part is here, these are absolute scale, clear, and absolute scale we always measure in Kelvin. So from here we can write TA divided by TB, this is equal to 200 divided by 350, clear. From here we can say this is equal to 10, we can say this is equal to 4, if we cancel with 5 then we can say this is 4 divided by 7, clear. So what is relation between temperature at A and B? This is equal to 4 by 7 and this is TB, clear. So relation between TA and TB, this is given by 4 by 7 times of TB, Clear to everyone? So this is all about this question. Now dear student, we are going to discuss this question, and this question is question number 11.3, and in this question it is given to you the electrical resistance in ohms of a certain thermometer varies with temperature according to appropriate law R equal to R naught 1 plus alpha T minus T naught. So dear student, this question is related to temperature dependency of resistance, number 1. Second thing, value of alpha is also given to you 5 into 10 to the power minus 3 per degree Celsius. Although in NCERT books value of alpha is not given, but they are assuming that you are going through this chapter, and in chapter value of alpha is given to you. So let's suppose I am giving to you this value 5 into 10 to the power minus 3 per degree Celsius. In this question it is given resistance is 101.6 ohm at triple point of water and 165.5 ohm at normal melting point of lead. Clear? So this alpha is the value of this lead. Clear? Now let us try to understand first this formula. Formula is given to you R is equal to R naught. Clear? R is equal to R naught 1 plus alpha T minus T naught. Clear? R is equal to R naught 1 plus alpha T minus T naught. Clear? So now we can say value of R. Clear? Listen carefully. This alpha is defined at temperature T naught. Clear? And this R naught is also defined at temperature T naught. Clear? Let's suppose I am saying this R naught, this temperature T naught is 0. At that time you can say this alpha is defined at value 0 degree Celsius and R naught is resistance at 0 degree Celsius. Clear? So from here you can say directly R equal to R naught 1 plus alpha T. Clear? But in this case, because the value of T naught is not provided to you, so we cannot assume this is to be 0. Clear? So now we can say first I am writing this value 101.6. So 101.6, this is equal to R naught 1 plus value of alpha is given 5 into 10 to the power minus 3 multiply this temperature T. This temperature is given to you triple point of water, so 273.16 minus T naught. Clear? And this is, let's suppose, equation number 1. Clear? Similarly we can write for this temperature 600.5 Kelvin. So we can say this 123.4 ohm, this is equal to R naught 1 plus value is given 5 into 10 to the power minus 3, and this temperature now we have 600.5 Kelvin minus T naught, and let's suppose this is equation number 2. Clear? So from here we can say our objective first is to calculate value of R naught and T naught. Clear? So how can we calculate value of R naught and T naught? Clear? For that one you can first divide equation number 1 with equation number 2. Clear? We can divide equation number 1 with equation number 2. So if I divide, I can write like this 101.6 divide 123.4. Clear? 123.4. Yes, this resistance is given to you 160. Okay, there is slightly mistake. Here we will write this resistance value is given at this melting point, this is 165.5. Clear? So I am writing here 165.5. Clear? Our objective in this question is to find temperature when resistance is 123.4. Clear? So for that one we can write like this 123.4, this is equal to R naught 1 plus 5 into 10 to the power minus 3. Clear? And we can say temperature is T minus, we can say temperature is T naught. Clear? So it means if we want to find exact value of R naught, we need to first calculate value of T and T naught. Yes or no? Clear? Yes. So from here you can see if we consider these two equations, definitely first I will divide 1 by 2. So I can write like this 101.6 divide 165.5. Clear? So 101.6 divide 165.5, and this is equal to what? This is equal to, we can say R naught and R naught is cancelled out, and this is 1 plus 5 into 10 to the power minus 3. 1 plus 5 into 10 to the power minus 3. Clear? And this is 273.16. Clear? So 216.16. Clear? 216.16. Just a minute. 273.16 value given. So I can say, just a minute. Yes. So from here we can see this is 273.16. Clear? 273.16 minus T naught. Clear? So this is minus T naught divided by, again we can write like this, 1 plus 5 into 10 to the power minus 3 and multiplied with, clear, multiplied with 600.5 minus T naught. So 600.5 minus T naught. Clear to everyone? So from here you can see, now we have to calculate and we have to find value of T naught. Now you can say, sir, calculation is very lengthy. Yes, definitely calculation is lengthy because the given data is like this, so we have to calculate. Clear? But actually you can take here some approximation, and if you are taking some approximation, the calculation may be simple. Clear? Let's suppose I am taking this is 100 and let's suppose this is 160 for example. Clear? Or you can say, yes, we can write like this, this is 100. Although we know this is not an exact way to solve this problem, but actually if you want to find, if you want to solve this equation, definitely we have to do some approximation. I am taking this is 100 divide by, and let's suppose I am taking this is 165. Clear? And this is equal to 1 plus 5 by 1000. 5 by 1000, this is 273.16 minus T naught. Clear? Divided by, this is 1 plus 5 by 1000, 600.5 minus T naught. Clear? From here if you are taking LCM 1000, so we can see, we can write like this, this is 100 divided by 165, this is equal to 1000 plus 5 multiply this one. Clear? So let's suppose I am taking this is 273 only. Clear? 273 means we can see this is 15, we have 1, this is 36, this is 3, so 1365 minus this is 5 T naught. Clear? Divided by, now I can say this is equal to 1000 plus 5 multiply, let's suppose 600, so this is 3000 minus this is 5 T naught. Clear? So if you cross multiply, after cross multiply you can find value of T naught. Clear? So from here you can say this is 1000 multiply 100. Clear? 1000 multiply 100 plus 100 multiply 3000 minus 5 T naught. Clear? It is equal to 165 multiply 1000. Clear? Plus 165 multiply 1365 minus 5 T naught. Clear? Now you can solve this problem. Clear? How can you solve? Just multiply it. Clear? Separate the value of T naught, and if you solve it, clear, definitely you can solve it. Definitely we can say this calculation will be little bit lengthy, but if you solve it you will find exact value of T naught. This is equal to minus 49.3 Kelvin. Always keep in mind we are already taken here some approximation, so that your value it may vary from this exact value. Clear? But this value you will find whenever you are taking this exact calculation. Clear? So value of T naught we are getting this minus 49.3 Kelvin. Clear? Now if you put this value T naught in any equation, let's suppose if you put in this equation, clear, you can easily calculate value of R naught. Yes or no? So from here you can write like this, 101.6, clear, 101.6, this should be equal to R naught. This is equal to R naught 1 plus 5 into 10 to the power minus 3. Clear? And we can say this is 273, you can say this is 273. So 273.16 minus, we can say this is plus 49.3, because T naught value is given to you in minus, so I am writing here plus. Clear? So now from here if you solve it, you will find value of resistance. Clear? Value of resistance you will find this is 38.9 ohm. Clear? Definitely we can do some calculation. Calculation is little lengthy, definitely we have, but if you solve it you will find resistance, this is equal to 38.9 ohm. Clear to everyone? Yes. Now my objective in this question is to calculate this one, value of temperature. So now we know value of R naught. Actually we also know value of T naught. Clear? So now I will utilize this equation. So I can write 123.4. This should be equal to R naught 1 plus R naught 1 plus 5 into 10 to the power minus 3, 5 into 10 to the power minus 3. Clear? And this is T minus T naught, and now you can put value of R naught and T naught. Clear? R naught value we have 38.9 and value of T naught you can put, this is minus 49.3 Kelvin. Clear? So if you write and then if you solve it, clear, you will find value of temperature T. Clear? And you will get this temperature T equal to 384.8 Kelvin. Clear? So let us try to understand this question. Actually, what is importance of this question? Importance is very clear. Whenever resistance is given to you, this resistance is given to you at triple point of water. Clear? So this alpha is defined for this T naught, R naught is defined for this one. Clear? So first you will calculate value of R naught and T naught. Clear? Alpha value is already given to you in a question. Clear? So when you find R naught and T naught, after that you can easily get the temperature at which resistance of that wire or that lead is equal to 123.4 ohm. Clear? So this is all about this question. Clear? So now dear student, we are going to discuss this question number 11.4. In this question we have to provide answer of the following statements. So number A part. In number A part it is given the triple point of water is a standard fixed point in modern thermometry. Why? Actually, initially we defined temperature scales, degree Celsius scale, Fahrenheit scale. Clear? And at the time we are defining lower fixed point and we can say upper fixed point. Let's suppose if we are talking about degree Celsius. So degree Celsius scale we are providing 0 degree Celsius as a ice point and we are defining steam point as 100 degree Celsius. Same as for Fahrenheit scale. For Fahrenheit scale we are defining 32 degree Fahrenheit as a ice scale and we can say that is steam point, that is 212 degree Fahrenheit. Clear? So we define these arbitrary scale on the basis of one assumption that atmospheric condition is not changing. Means let's suppose if I changes external conditions, let's suppose pressure, at the time we can say this value of ice point and steam point is changes. Clear? It means we can say on our external condition boiling point and the melting point depends. Clear? So as the external condition changes, the value of fixed point that we have already defined, that is changes. That's why we now come to point that we are taking reference as we can say triple point of water. Why? Because triple point of water is independent of some external condition. Clear? We know if we are talking about triple point of water temperature, that is 0.01 degree Celsius. So that value remain fixed irrespective of external conditions are changing or not. Clear? So that's why we can say in modern thermometry we are taking triple point of water as a standard fixed point. Clear to everyone? Now what is wrong in taking melting point of ice and boiling point of water as standard fixed point? Clear? I already told you, as external condition changes we can say boiling point and the melting point changes. For example, if you talk about a term that is regulation. Clear? So in regulation what will happen? If we are increasing pressure, melting point of ice decreases. That's why we can say at 0 degree Celsius ice melt in external loading condition, or we can say in external pressure condition. Clear to everyone? Clear? Same you can take another example. Let's suppose you are on the hilly stations. So on the hilly station we know external pressure is less. So at that time boiling point decreases. Clear? That's why it is very difficult to cook any vegetables or food. Clear? So this we can say that's why we are using this triple point of water as our reference. Clear to everyone? Yes. Now we are going to discuss part number B. So in part number B, it is given there were two fixed points in original Celsius scale and mentioned above, which were assigned the number 0 degree Celsius and 100 degree Celsius respectively. Fine. On the absolute scale, one of the fixed point is triple point of water that we have already included in modern thermometry. clear, which on the Kelvin scale provide a number 273.16 Kelvin, or we can say this is equal to 0.01 degrees Celsius. It is an information that is given to you in this question. What is the other fixed point on this Kelvin scale? Now listen carefully. How this Kelvin scale is determined. Clear? First let us try to understand that one. Clear? Listen carefully. So if we talk about Charles' law, we can say volume of a gas is directly proportional to temperature. Clear? So if you draw here a graph, between volume and the temperature, clear, and this temperature is in what? This is in degrees Celsius. Clear? So if you are talking about, this is temperature in degrees Celsius, and if you draw here graph, this graph will be like this. It is a straight line. So if you extend this line, clear, you will find this point B, and this is a point at which you can see volume of gas becomes 0. Clear? Volume is become 0. Clear? It means we can say all molecular motion stops at this point. Clear? So actually one reference we are providing at 0.1 degrees Celsius. This is triple point of water, 273.16 Kelvin. Clear? On absolute scale we are taking 0 degrees Celsius. On absolute scale we are taking 0 degrees Celsius as our reference, and this is 273.15 Kelvin. Clear? But actually we can take one more fixed point here. Clear? And that point is actually 0 Kelvin. Clear? Or you can say this is equal to minus 273.15 degree Celsius. Clear to everyone? Clear? Why I am taking 0 Kelvin as our reference, another reference for an absolute scale? Because all molecular motion stops at 0 Kelvin. Why? Because volume becomes 0. It means we can say there is no gas molecule. No gas molecule means we can say volume is 0, pressure is 0, and we can say we can take it as also a reference. Clear? So this is all about, we can say, part number B. Clear to everyone? Yes. Now we are going to discuss part number C of this question, and in this question it is given the absolute temperature T is related to the temperature in Celsius scale is given by T minus 273.15. Yes. So from here you can say actually we define T degree Celsius. If we define T degree Celsius, or we can say this is TC, it is defined as temperature in Kelvin minus 273.15. Clear? Now in this question it is given, why do we have 273.15 instead of 273.16? Clear? Because if you are taking triple point of water as a reference point, why are you not taking 273.16? Now let us try to understand. Let's suppose I am taking here, if I am talking about Celsius, we are talking about temperature scales. This is 0 degrees Celsius, this is what, 100 degrees Celsius. Clear? Clear? From here you can say we are taking 212. If we are talking about Kelvin scale, on the Kelvin scale we are taking this is 273.15 Kelvin. Clear? And here this is what, 273.15 Kelvin. Now listen carefully. Let's suppose if I am drawing here this one, let's suppose here we have temperature Tc, and let's suppose here we have temperature capital T. Clear? So how can we define temperature scale? We always write like this, Tc minus 0, this should be equal to, or we can say this is divided by 100 minus 0. Clear? And this should be equal to, we can say T minus 273.15 divided by 373.15 minus 273.15. Clear? So from here we can say this is equal to Tc by 100, and this should be equal to T minus 273.15 divided by 100. Clear to everyone? So from here you can say this one and this one cancel out, and you can write Tc equal to T minus 273.15. Clear? So this expression we are getting whenever we are taking our lower limit at 0 degrees Celsius. Clear to everyone? But let's suppose if I am talking about triple point of water. Clear? So whenever I am talking about triple point of water, at that time I will take this lower limit at this point. Clear? And here we can say this is 0.01 degrees Celsius. Clear? Correspondingly you will find here this is 273.16 Kelvin. Clear? So at the time if you write, how can you write like this? We can say, if you see that if you are taking 0.01 degree Celsius, here we will subtract first Tc minus 0.01 degree Celsius, and here you will write T minus 273.16. Clear? So again you will find same relation. Let us try to understand what I am saying to you. If I write like this, Tc minus 0.01, this should be equal to T minus 273.16. Clear? Let's suppose you are saying why we are not taking 273.16. So let's suppose if I take here 273.16. Clear? So from here we can say value of Tc, this is given by T minus 273.16 plus 0.01. Clear? So from here we can say Tc, this is given by T minus 273.15. Clear? Yes or no? So from here we can say actually we are getting same result. That's why we always use 273.15, or sometimes for the ease of calculation we provide only 273 here. Clear? So this is all about this question. Clear to everyone? C part is complete? Yes. Now we are going to discuss part number D. So in part number D it is given what is the temperature of triple point of water on an absolute scale. Definitely we know 273.16 Kelvin, which unit interval size is equal to that of Fahrenheit scale. Now listen carefully. Clear? Actually if I again draw this scale, at the time we know lower limit is 0 degree Celsius. For Celsius scale this is 100 degree Celsius. Here we can say 273.15 Kelvin, this is 373.15 Kelvin. Clear? And unless suppose if I am talking about Fahrenheit scale, this is 32 degree Fahrenheit, 212 degree Fahrenheit. Clear? Now we are talking about one important concept. What is important concept? This difference we have for 100, here we have difference for again 100, and here we have difference for 180. Clear? So from here you can see, we can write like this: 100 degree Celsius difference, this is equal to 100 Kelvin, and this is equal to 180 degree Fahrenheit. Clear? So from here we can see difference in 1 degree Celsius, it should be equal to 1 Kelvin, and it should be equal to 180 by 100 degree Fahrenheit. Clear to everyone? So from here we can see 1 degree Celsius, this should be equal to 1 Kelvin, and this should be equal to 9 by 5 times of degree Fahrenheit. Clear to everyone? Now we can say in this question what is given to you. In this question it is given what is temperature of triple point of water on Fahrenheit scale. So we say, let's suppose if you are talking about temperature, or we can say Fahrenheit scale. So 1 Kelvin this is equal to 9 by 5 times of degree Fahrenheit. Clear? So if you are talking about triple point of water, that is 273.16 Kelvin. Clear? 273.16 Kelvin. So this should be equal to 9 by 5 times of 273.16, and this is what? Degree Fahrenheit. Clear? So from here we can say, if you are multiplying 9 with 273.16, clear? So we can say this is equal to, we have 9 6 54, we have 5, so this is what? 14, we have 1, this is 28, we have 2, 9 7 63, we have 5, then we have 6, so 18 and 6, this is 24. Clear? It is divided by 5. Clear? So from here if you cancel, if you divide it, you can see this is what? 4, we have 4 left, we have 9, 1, we have 3 left. Clear? This is 6, and we have 4, and again 9 degree Fahrenheit. Clear? So I can say, if we are talking about yes, if we are talking about 1 Kelvin is equal to 9 by 5 times of degree Fahrenheit. If I am talking about of triple point of water corresponds to 273.16, then corresponding to this one we are having reading in degree Fahrenheit, this is equal to 491.69 degree Fahrenheit. Clear to everyone? So this is all about this question. Dear student, now we are going to discuss this question number 11.5. In this question it is given to you, two ideal gas thermometer A and B use oxygen and hydrogen respectively. Fine. The following observations are made. Temperature is given to you, triple point of water corresponding triple point of water and normal melting point of sulfur. these temperatures are given to you, and this is given to you for thermometer A and thermometer B. Clear? In thermometer A we are using oxygen, and in thermometer B we are using hydrogen. Clear to everyone? Now it is given here that pressure thermometer for oxygen, it is showing this reading for triple point of water and normal melting point of sulfur. Clear? The same if we are talking about pressure thermometer, this is showing result for hydrogen. Hydrogen for triple point of water is this one, and for normal melting point of sulfur is this one. Clear? Now what is our question? Number A, what is absolute temperature of normal melting point of sulfur as read by thermometer A and B? Clear? Now listen carefully. Let's suppose if I assume initially oxygen and hydrogen as an ideal gas. Clear what I am saying to you? We are assuming oxygen and hydrogen as an ideal gas. So we know whenever we are talking about gas thermometer, clear, gas thermometer, and especially if I am talking about constant volume gas thermometer, so at that time we can say for constant volume gas thermometer, clear, we know for an ideal gas PV equal to nRT. Clear? If we are talking about constant volume, so pressure is directly proportional to absolute temperature. Clear? So first we will calculate absolute temperature for normal melting point of sulfur. Clear? Read by thermometer A. Clear? So concentrate. Actually I will utilize this concept P divided by PTR. This should be equal to T divided by TTR. Yeah, actually PTR and TTR, what is this? This is what pressure corresponding to triple point of water, and this is what temperature corresponding to triple point of water. Clear? Now our objective in this question is to calculate temperature at melting point, normal melting point of sulfur. So we can write like this: T, this should be given by P divided by PTR multiply, we can say this is TTR. Clear? Now now if you concentrate here, pressure at triple point of water is given 1.250 into 10 to the power 5. So we can see 1.250 multiply 10 to the power 5. 10 to the power 5. Clear? Now if you are talking about pressure, how can we utilize this pressure? Pressure is given, this is 1.797 into 10 to the power 5 Pascal. So 1.797 into 10 to the power 5 Pascal. Now you know very well what is triple point of water, 0.01 degree Celsius. So this is equal to 273.16. Clear? So from here you can say this one and this one is cancelled out. Clear? And we can see near about, if you calculate, let's suppose I am saying this is 1.8 and let's suppose this is 25 by 2. We can write like this. Clear? And actually this is 2.5 divided by 2. Clear? And it is multiplied with 273.16. Clear? From here you can say this one and this one cancel out. Clear? And we can see, let's suppose if I write this is 12.5. Clear? If you do here near about calculation, clear? So 18 divided by, let's suppose I am taking 12 only. Clear? So this is near about 1.5. Yes or no? And this is 273.16. Clear? Clear? So from here we can see, if you divide here, you can also write 3 by 2. This is 273.16. Now if you multiply 3 with 273.16, we can see this is 48. Clear? This is what? 9. And we can say this is 21. This is 2. So 819.48 divided by this is 2. Clear? So from here we can say this is 4, 0. Now we can say this is 9. Clear? This is 9. We can say 18. So we have one left. This is 7 and this is 4. Clear? And this is in Kelvin. This is, my dear student, this is approximate value. This is not an exact value because for calculation we are doing some approximation. Clear? Similarly, actually we can say this is for what? This is for, we can say, oxygen. Clear? So normal melting point, normal melting temperature for oxygen. So we can say this is only for oxygen. Clear? Now same we can repeat it for hydrogen gas also. Yes or no? So from here we can see for hydrogen. Clear? So if I am talking about hydrogen, again I will apply same formula, that T is equal to P divided by PTR multiply TTR. Clear? So from here we can see pressure corresponding to normal melting point, this is 0.287 into 10 to the power 5, clear. So 0.287 into 10 to the power 5 divided by, now what about pressure at triple point of water, this is 0.200 into 10 to the power 5, clear. 0.200 into 10 to the power 5 and multiply, clear. So multiply, if we multiply it, what triple point of water, this is equal to 273.16 Kelvin, clear to everyone. So from here we can say this one and this one, it is cancelled out, clear. And from here we can say this is 287 divided by, and we can say this is 200 into 273.16, clear. So from here you can write like this, this is 2.87 divide 2 into 273.16, clear. So from here near about you can say this is 1.4, so 1.4 into 273.16, clear. 1.4 you can write like this, this is 14 by 10, clear. This is equal to 7 by 5, so 7 by 5 into 273.16, clear. So if I multiply 7 into 273.16, clear, what is its value? Now we can say we have 2, we have 4, 11, we have 1, this is 22, again we have 2, this is 51, we have 5, 7 to 14, 5, 19, clear, and it is divided by 5 and this is dot, clear. From here we can say this is equal to what? We can say this is 15, then we have 3, so we have 4 left, this is 8, clear, 8, so we can say here we have left 1 and yes, this is 5, 3, 15, we have 4, 8, 1, we can say this is 2, clear, and 2 means we can say that is 5, 15, we have 3, 8 and yes 2, we mean 2, we can say 4. So from here we can say we are getting temperature 382.4 Kelvin, and actually if you will not take here approximation, you also find here this value is near about 385 Kelvin, near about, clear, if you not take approach. Actually one more question that is asked here, what do you think is the reason behind slight difference in the answers of thermometer A and B? Actually if you are taking both as an ideal gas, the answer should be same, yes or no? But why there is some difference is to be coming in the value of temperature. Here you are getting approximately, because you take approximation, that's why you are getting this value, otherwise it will be near about 385 Kelvin, clear, and this is 382.4 Kelvin. Why you are getting this difference? Because we assumed hydrogen and oxygen as an ideal gas for this question, but actually they are not an ideal gas, clear. It means they are actually showing some, we can say, deviation behavior or deviated behavior from an ideal gas, clear. So this is all about this question, clear. Now dear student, we are going to discuss this question number 11.6, clear. In this question it is given to you, a steel tape 1 meter long is correctly calibrated for a temperature of 27 degree Celsius, clear. It means at 20 degree Celsius steel tape is correctly calibrated, means this is length of that steel tape equal to 1 meter, or we can say 100 centimeter, fine. The length of a steel rod measured by this tape is found to be 63 centimeter on a hot day when the temperature is 45 degrees Celsius. Now listen very carefully. Actually if you observe, from 27 degrees Celsius to 45 degrees Celsius temperature is increasing. So whenever temperature is increasing, definitely there will be some expansion is to be take place in steel tape, clear. And it is given the length of steel rod is to be measured, this is equal to 63 centimeter. It means actually if you are talking about actual length of that rod, is definitely it will be more than 63, yes or no? Are you going to relate this condition what I am saying to you? If temperature increases, again what I am saying to you I am writing here, clear, at T equal to 27 degrees Celsius, length of steel tape, this is equal to 1 meter or this is equal to 100 centimeter, clear. Whenever we are talking about temperature 45 degrees Celsius, so at 45 degrees Celsius we can say temperature is we can say temperature is increasing. Temperature increases. When temperature increases, I can see length of tape is also increases. Clear? So what is tape? We can say the tape that is measuring that steel rod increases. Clear? It means I can see reading of length of steel rod measured is less than reading of length of steel rod measured, it is less than compared to, we can say, its actual length. Yes or no? Why this is happening? Because there is an expansion is to be taking place on the steel rod. Clear? On the steel tape. Clear to everyone? So now can we find what is elongation is to be take place in steel tape? Clear? So first I am talking about elongation in steel tape. Clear? So I can say delta L, this is given by L alpha delta T. Clear? Length. So definitely length is given to you 1 meter, but I am just talking about 1 centimeter, because if I know what is elongation in 1 centimeter, at that time I can relate the total elongation or total length of actual length of this rod. Clear? So let's suppose I am taking one division of this steel tape, that is 1 centimeter. Clear? Alpha value is given to you in this question 1.20 into 10 to the power minus 5. 1.20 into 10 to the power minus 5. Clear? And multiplied with delta T. Delta T means we can say temperature difference. Clear? Temperature difference we have from 45 to 27. Clear? So from here we can say this is given by 1.20 into 10 to the power minus 5 into, we can say this is equal to 18. Clear? So if you write here 18 multiply 1.2, so we can say this is 6 by 5. Clear? 6 by 5 into 18 into 10 to the power minus 5. Clear? So now if you multiply 18 with 6, we can say this is what, 8, we have 4, so this is 10, divide by 5 into 10 to the power minus 5. Clear? From here if you calculate, you can see you are getting this value 2, we can say 1. Clear? And we have 6. Clear? So 5 to 10 we have 21.6. Clear? Into 10 to the power minus 5 centimeter. So this is what? This is elongation in steel tape. Clear to everyone? Yes. So from here you can write this value like this, delta L. Delta L is given by 21.6 into 10 to the power minus 5 centimeter. Clear? And this is equal to what? We can say 0.000216 centimeter. Clear to everyone? Now can I find what is actual length? Okay, first read this question. Here it is given, the length of steel rod measured by this tape is found to be 63 centimeter on a hot day. Okay, when the temperature is 45. What is the actual length of steel rod? Clear? So we can find now actual length of steel rod. Clear? Now we know, actually we find here, this is what? This is elongation in steel tape, one division of steel tape. So actually what is length of one division of steel tape? This is equal to what? Actually we know at 27 degrees Celsius this is equal to 1 centimeter, but at 45 degrees Celsius, so at 45 degrees Celsius it should be multiplied with, or we can say actually we have to add this elongation also. Yes or no? So from here we can say, just a minute, if I write actual value of one division at 45 degrees Celsius, it should be 1 plus 0.000216. Clear? And multiplied with the total number of division on steel tape we have 100. So this is equal to 1.000216 multiplied with 100 centimeter. Clear? So now we can say this is actual length of steel tape at 45 degree Celsius. Clear? So length of one division of steel tape is what? This is 1.000216, and if we total find length of steel tape at 45 degrees Celsius. Clear? If we find length of, just a minute, if we find length of steel tape at 45 degrees Celsius, steel tape at 45 degrees Celsius. Clear? So it should be 100.0216 into yes, clear? This is centimeter. Clear? 100.0216 centimeter. So this is actual length of steel, we can say steel tape at 45 degree Celsius. Now what is our objective? Our objective in this question is to find the length of steel rod. The length of steel rod. Actually we find this is what? This is length of steel tape. Clear? Now we know length measured of steel rod at 45 degrees Celsius, this is equal to 63 centimeter. But if we are talking about actual length, because we know if we are increasing temperature means one division value of steel tape is increasing, so actual length of the rod, it should be greater than the measured length. Clear? So from here you can say we can multiply this 63 with, clear, we can say one division of this steel tape. Clear? So this is equal to 1.000216. Clear? So from here if you multiply, you can say 63 point. Clear? If you multiply 216 with 63, this is equal to what? 18, we have 1, 4, this is 6, we can say 36, this is equal to what? 9, and this is 8. So 8, we can say this is 10, 7 and 9, this is 16, this is 9608. Clear? So 0.9608, so 0900, just a minute, this will be 0.9608 centimeter. Clear? So this is actual length of steel rod at 45 degree Celsius. Clear? Now it is also asking in this question what is length of same steel rod on a day when the temperature is 27 degree Celsius. So at 27 degree Celsius, actually this steel tape is correctly calibrated. Clear? At 27 degrees Celsius, this steel tape is correctly accurate, means one division of this steel tape, it provides value of 1 centimeter. Clear? So if you are measuring 63 centimeter length, then it will be equal to exactly 63 centimeter. Yes. So from here we can say at 27 degrees Celsius, length of steel rod, this is equal to 63 centimeter. Clear? This is equal to 63 centimeter. Clear to everyone? Now dear student, we are going to discuss this question number 11.7, and in this question it is given to you a large steel wheel is to be fitted on to a shaft of the same material. Okay, at 27 degrees Celsius, the outer diameter of shaft is given to you 8.70 centimeter. So let's suppose I am saying value of L1, this is 8.70 centimeter, it is given in this question, and the diameter of the central hole of a wheel. Clear? So we can say, let's suppose this is L2, 8.69 centimeter, it is given. The shaft is cooled by using dry ice. At what temperature of the shaft does the wheel slip on the shaft? Now listen carefully, what is concept behind it. Now you can say, let's suppose here we have this is wheel. Clear? Let's suppose this is wheel. Clear? And we can say inner diameter of that wheel is given to you. Clear? The inner diameter is given, this is 8.69 centimeter. Clear? And we have one shaft, and let's suppose we want to fix that shaft on this wheel. Clear? At that time we can say, because diameter is now given to you 8.70, so it will be just outside of the inner diameter of this wheel. Clear? Now what I want that this shaft slip on this wheel when this happen. So for that one we are actually using here dry ice, and dry ice is actually contracting this material, clear, and it means we can say the diameter of this shaft is decreases, clear. So from here you can see, can we write like this, this delta L is equal to L2 minus L1, clear. So L2 value is given 8.69 minus 8.70, clear. So for that we can say this is equal to minus 0.01 centimeter, clear. So from here what is our objective in this question? At what temperature of the shaft the wheel slip on this shaft, clear. So from here you can write like this, delta L equal to L1 alpha delta T, clear. From here we can say delta T, this should be equal to delta L over L1 alpha, yes or no. So from here delta L is minus 0.01 centimeter divided by L1 is given to you 8.70 multiply. What about alpha value is given 1.20 into 10 to the power minus 5, clear, 1.20 into 10 to the power minus 5. So from here we can write like this, delta T, this is given by minus, we can say 1 divided by, this is 8.7 into 1.2 into 10 to the power minus 3, clear, we can write like this. So from here you can see, near about if I talk, this is 1000 minus 1000 divided by, I am taking it near about 8, clear, 8 into, we can say this is 1.2, we can say this is 6 by 5, clear. From here we can say this is 125, although I can say this is 9, near about 9, but for calculation I am taking this is 8, so minus 125. So from here you can see, you can write like this, delta T is equal to minus 125, and we can say this is 5 by 6, clear. So from here we can say minus 2 0, we can say 6 8, clear, multiplied with 5. So this should be equal to, this difference it should be equal to, we can say this is 40, we have 4 and this is 10, yes or no. So this is my 104.0, clear, this one, clear, 104.0, clear. This is value of delta T. Now what is our objective? Our objective is to calculate temperature. So we can see temperature, this is given by T1 minus T2, and this should be equal to, clear, this should be equal to 104, approximate this value 104. So from here we can say initial temperature is given to you, yes, at 27 degree Celsius, clear. So at 27 degree Celsius, oh okay, actually we are writing here this delta T, yes, and here we write L2 minus L1, okay. So dear student, if I write this expression, that is delta T is near about this value, this is 104, clear, because we are decreasing this temperature, clear. So definitely we can say this is T1 minus T2, this should be equal to 104. So from here you can write like this, T2 equal to T1 minus 104. Actually this 104 is difference, either you can take in degree Celsius or in degree Kelvin, but let's suppose if I am writing this value, because temperature is given to you 27 degrees Celsius, so 27 plus 273 minus 104. Actually we have to add here 273.15, but for calculation we are taking only 273. So this is equal to 300 minus 104, clear, and it will be near about, we can say this whatever value we will find, this value will be in, we can say Kelvin, yes or no. So from here you can say this is near about, we can say 6, and this is 9, and this is 196 Kelvin, clear. So this is the temperature at which we can say this shaft is actually slip on this wheel, clear. So this is all about this question. Now dear student, we are going to discuss this question number 11.8, and in this question it is given to you, a hole is drilled in a copper sheet, clear, okay, a hole is drilled in a copper sheet. The diameter of hole is 4.24 centimeter at 27 degrees Celsius. So we can see value of diameter, it is provided to you 4.24 centimeter at temperature, we can see 27 degree Celsius, clear. What is the change in the diameter of hole? Means our objective first is to calculate value of D2, when the sheet is heated to a temperature of 2 to 7 degrees Celsius. So T2 value is given 227 degree Celsius. Clear? Now our objective in this question is to find this change in diameter. Clear? Change in diameter means we will find delta D, or we can say this is D2 minus D1. This is what? Clear? Coefficient of linear expansion of copper. So alpha for copper, it is provided to you 1.70 into 10 to the power minus 5, and this is Kelvin inverse. Clear to everyone? Now how can we find? Actually we know, because we are just talking about diameter. Clear? So whenever temperature increases, diameter increases, and that expansion is actually given by this formula delta D. This is given by, we can say, D1 alpha delta T. Clear? It is just like a formula you write delta L equal to L alpha delta T. Clear? From here we can say, we can write like this, delta D, this should be equal to D1. D1 is given to you in centimeters, so this is 4.24. Clear? Value of alpha 1.70 into 10 to the power minus 5 multiply. Clear? What about delta T? Delta T is given to you 227 minus 27. Clear? So from here we can say this is 4.24 into 1.7 into 10 to the power minus 5 into 200. Clear? This is 200. So if you see, if you remove from here this 100, this is cancelled out. Clear? From here we can say this is 848 into 1.7 into 10 to the power minus 5. Clear? And this value is in centimeter. Clear? So from here you can say, if I remove this decimal also, we can write this is 10. If you multiply that 848 into 17, so 848 into 17, we can say this is 56, we have 5. Clear? So 7 4 28, we can say this is 33, this is 3, 8 7, this is 56, so this is 59. Multiply, we can say this is equal to 8 4 8. Clear? From here you can say this is 6, this is 11, we have 10, 14, we have 1, this is 14. Clear? So 144.16, so 144.16 into 10 to the power minus 6 centimeter. Clear? Or you can also write like this, this is equal to 14.4 into 10 to the power minus 3 centimeter. Clear to everyone? So this is what? This is change in diameter when temperature changes from 27 degrees Celsius to 2 to 7 degrees Celsius. Clear to everyone? So this is all about this question. Now student, we are going to discuss this question, and this is question number 11.9. In this question it is given to you a brass wire 1.8 meter long at 27 degrees Celsius is held taut with little tension between two rigid support. Clear? So let's suppose if I am drawing, let's suppose this is one of the rigid support, this is another one of rigid support. Clear? Let's suppose a wire is connected between these two, we can say between these two fixed end. Clear? The length of this wire is given to you, value of L, this is 1.8 meter. Clear? 1.8 meter long, and temperature T1, this is provided to you 27 degree Celsius. 27 degree Celsius is held taut with little tension between two rigid support. Fine. If the wire is cooled to a temperature of minus 39 degrees Celsius, so temperature T2, this is given minus 39 degree Celsius. Clear? Then what is the tension developed in this wire if the diameter of this wire is 2 mm? It means diameter value is given 2 mm. Clear? When diameter is given, it means we can write radius, this is 1 mm. Clear? Coefficient of linear expansion is also given to you, and coefficient of linear expansion alpha, I am writing this alpha value, alpha equal to 2 into 10 to the power minus 5 per Kelvin. Clear? And Young's modulus also given, Y value, this is 0.91 into 10 to the power 11, and this is Pascal. Clear? Now listen, how to approach this question, that is very important. Clear? First of all, concentrate on the objective part of this question. Objective of this question is to calculate tension developed. Clear? How can we calculate tension? Before that one, you can analyze here one concept. It is already given at length of this wire that is fixed at both rigid support, that is 1.8 meter at 27 degrees Celsius. Now let's suppose what I am doing, I am decreasing temperature. So when I am decreasing temperature is minus 39 degree Celsius, clear? So can we find here total change in temperature? Yes or no? Actually what I am doing here, I am decreasing temperature. So whenever I am decreasing temperature, at that time this length, we can say this wire, it will try to compress, or we can say it will try to shorten its length. Yes or no? But actually here we have rigid support, so definitely I can say the tension force is to be developed. Yes or no? So from here you can say tension force is developed on this rigid end, clear? It means we can see our objective in this question is to calculate that tension, but how can we calculate? Actually we know we know one relation, delta L is equal to L alpha delta T, clear? So from here can we write like this, delta L by L, this should be equal to alpha delta T. Now you know this delta L by L is what? Actually this is change in length upon original length, clear? It means we can say this is what? This is strain, yes. So from here we can say this is value of strain, clear? So we can say strain, this is given by alpha delta T, clear? Strain value is given by alpha delta T, clear to everyone? So strain value is alpha delta T. Now what is strain, clear? So for that one, alpha value of this brass wire, it is given to you 2 into 10 to the power minus 5 and multiplied with what is change in temperature, clear? Change in temperature you can say 27 minus 39, clear? So 27 plus 39, clear? So what about total? I can say this is 2 into 10 to the power minus 5 multiplied. Now we can say let's suppose 30 plus 20, 50, 57 and 57 and 9, we can say 66. Yes or no? 66, clear? So if you multiply, you can say this is equal to 132 into 10 to the power minus 5, clear? So this is what? This is value of strain, clear to everyone? Clear? So this is value of strain. So from here actually we can see we also know one relation, Young's modulus. Young's modulus is given by stress over strain, clear? So now we can say whenever we are decreasing temperature, at that time tensile stress will be generated, clear? So from here you can say value of stress, this is equal to Y multiply this is strain, clear? Value of Y, clear? Value of Y is given 0.91 into 10 to the power 11. So 0.91 into 10 to the power 11. And what about strain, clear? What about strain? So I can say strain value given 132 into 10 to the power minus 5. 132 into 10 to the power minus 5. So from here we can say this is 91 by 100 into 132 multiply 10 to the power 6, clear? And this value we have in Newton per meter square, or we can say this is Pascal. So from here we can say, can you multiply 132 with 91? Yes. So 132 91, directly you can say this is 2 3 1, this is what? 18, clear? We have 1, so we can say 28, we have 2, this is 11, 2, we can say 11, we have 1, so this is 10. So 12012, clear? 12012 multiplied with 10 to the power 4 Newton per meter square. So this is value of tensile stress. But what is our objective? Our objective in this question is to calculate value of tension. So from here actually we know stress is what? Stress is defined as internal resisting force per unit area, clear? So from here we can say tension divided by area, this is equal to 12012 into 10 to the power 4. So from here you can say 12012 into 10 to the power 4 multiply what about area, clear? So what about area? So area we can see here radius is given to you 1 mm. So we can say this is pi into and we can say this is 10 to the power minus 3. So 10 to the power minus 3 whole square. Yes or no? So from here we can say tension value is given 12012 into pi into, I can say this is 10 to the power minus 2 and this is Newton. Yes or no? Yes. So from here, if you multiply it with 3, approximately you can say, let's suppose this is 3, clear? So 6, 3, 0, we can say 6, 3, clear, into 10 to the power minus 2 Newton. So from here we can say we are getting this tension approximately equal to 360.36 Newton, clear? So this is all about this question, clear to everyone? Now student, we are going to discuss this question number 11.10. In this question it is given to you a brass rod of length 50 cm and diameter 3 mm is joined to a steel rod of same length and diameter, clear? So from here you can see, let's suppose we can see, let's suppose these are the two rods, clear, and two rods are connected like this, clear? A brass rod of length, so length is given, so L1, and let's suppose this is L2, clear? According to given question, value of L1 equal to L2 and this is equal to 50 cm, fine. And value of diameter is also given, D1 equal to D2, this should be equal to 3 mm, clear? Let's suppose this is 1 and this one is 2. 1 I am denoting for brass and 2 I am denoting for steel rod, clear? Now it is also given. Now what is our objective? Our objective in this question is to calculate what is change in length. What is the change in the length of the combined rod at 250 degree Celsius. Now okay, if the original length is at 40 degree Celsius, means the length of this length of brass rod and steel rod is given to you at 40 degree Celsius, and now our objective is to calculate this length at 250 degree Celsius, clear to everyone? Yes. So now if we say, is there a thermal stress developed at a junction, clear? Now our objective in this question is to calculate thermal, we can say thermal stress, clear? So how can we calculate thermal stress? That is very, very important, clear? So first of all, let's calculate what is change in length of combined rod. So first of all, we find the change in length of brass rod, clear? And this should be equal to L alpha for brass, clear? And this is delta T, value of length. So I can say this length is L1, I will consider, so 50 cm means, okay, directly I am writing this value in terms of centimeter only, clear? So let's suppose this is 50 multiply value of alpha of brass, clear? It is given 2 into 10 to the power minus 5, clear? And now what is change in temperature? Change in temperature 250 minus 40, this is equal to 210, clear? From here you can say this is 100, so 210 into 10 to the power minus 2 and this is what? Centimeter, clear? From here we can say this is what? 100, clear? 100 means this is 10 to the power minus 3, yes, clear? This is 100, this one 10 to the power minus 3, 210. So from here we can say this is 0.210 centimeter, clear? And from here you can say change in length of brass rod we are getting 0.21 centimeter, clear? But what about change in length of steel rod, clear? Change in length of steel rod, this is given by L2 alpha for steel and this is delta T, clear? So value of L2 is given, same value we have 50 centimeter, but what about coefficient of linear expansion for steel? This is 1.2 into 10 to the power minus 5, 1.2 into 10 to the power minus 5 and multiplied with what about delta T? Delta T is given again 210, clear? From here you can say this is what 60 into 10 to the power minus 5 into 210, clear? From here you can see this is equal to 6 into 21 into 10 to the power minus 3, clear? From here we can say this is 136, clear? So 126, clear? This is equal to what? 126 multiply 10 to the power minus 3. From here you can say this is equal to 0.126 centimeter, clear? Or we can say if we find up to same significant figure, at that time you can say this is 0.13 centimeter, clear? Because both rods are connected one to one, or we can say both rods are connected in a series. So how can we calculate total elongation, clear? So I can write like this, total elongation, this is given by delta L1 plus delta L2, clear. So what about delta L1? Clear? Delta L1. Delta L1 is given to you. This is equal to 0.21 centimeter. So 0.21 centimeter plus this is 0.13 centimeter. Clear? So this is equal to 0.34 centimeter. Clear everyone? So this is what? This is total change in length 0.34 centimeter. Clear? Okay. We have now one more question. What is that question? We can say, is there any thermal stress developed at a junction? So now you can say, actually we are changing temperature, but there is no any restriction. Clear? Or we can say here rods are actually having free expansion. So in the case of free expansion, because there is no restriction, so I can say there is no thermal stress is to be developed. Although I can say thermal strain is developing. Clear? Whatever you are calculating here, this is thermal strain. Clear? Actually this is change in length. If you divide with total length, you will find thermal strain. Clear? But there is no thermal stress because there is no compressive or tensile stresses are developed. Clear? So I can say because of free expansion, no thermal stress is developed. Clear to everyone? So this is all about this question. Clear? Now dear student, we are going to discuss this question number 11.11. Clear? In this question it is given to you, the coefficient of volume expansion of glycerin is 49 into 10 to the power minus 5 Kelvin inverse. Clear? What is the fractional change in its density for a 30-degree rise in temperature? Clear? So now dear student, you know there is a relation between density and we can say this is volume expansion. Clear? So rho is given by rho naught 1 plus gamma delta T. Yes or no? This is a relation between density and volume coefficient of volume expansion. Clear? From here you can write like this: rho naught, this is equal to rho 1 plus gamma delta T. Clear? So from here we can see rho naught equal to rho plus rho gamma delta T. Clear? Now what is our objective in this question? Our objective in this question is to calculate fractional change in density. Clear? So can we write like this: rho minus rho naught divided by rho. This is equal to minus times of gamma delta T. Yes or no? Yes. So from here we can say, if you see that density initially is high, as you are increasing temperature, because it is given in this question that there is a rise in temperature. So when there is a rise in the temperature, it means we can say density decreases. Clear? That's why we can say this rho is less compared to rho naught, and definitely we are getting this value negative. Clear? So our objective in this question is to change fractional change in density. So delta rho divided by rho, this is given by minus gamma delta T is equal to minus. Now what is value of gamma? Gamma is given 49 into 10 to the power minus 5, and what about delta T? Delta T is given, this is 30 degree. Clear? So from here we can say this is equal to what? Minus, we can say 93, this is 27, now we have 2, so 147 into 10 to the power minus 5. Clear? So this is fractional change in density. Clear to everyone? So yes, from here you can say delta rho by rho, this is equal to minus 147 into 10 to the power minus 5, or you can say 1.47 into 10 to the power minus 3. Clear? So this is fractional change in density. This is all about this question. Now dear student, we are going to discuss this question number 11.12. Clear? In this question it is given to you, a 10 kilowatt drilling machine. A 10 kilowatt drilling machine is used to drill a bore in a small aluminum block of mass 8 kilogram. Clear? So from here you can say power of this drilling machine is provided to you 10 kilowatt, or we can say this is 10 into 10 to the power 3 watt. Clear? Now it is used to drill a bore in a small aluminum block of mass. Clear? So mass is given to you, that is 8 kilogram. Clear? 8 kilogram. How much is the rise in the temperature of a block in 2.5 minutes? Clear? So time is given to you 2.5 minute. Clear? So we can convert this into second. So 2.5 into 60 seconds. Okay. Now, can we find here total energy that is given by this drilling machine? Yes, we can calculate this energy by Q equal to PT, means power multiplied time. Clear? Value of power we have 10 into 10 to the power 3. This is what? Joule per second. Clear? And multiplied with what about time? Time is given 2.5 into 60. So we can say this is 5 by 2. So 5 by 2 means we can say 300. It means 150 second. Yes or no? Clear? 2.5 minutes. So this is 150 second. So from here you can say this one and this one cancelled out. From here we can write 15 into, we can say 10 to the power 5. Clear? This is joule. Clear to everyone? So 15 into 10 to the power 5 joule. This is value of Q. Clear? So this is clear. This is value of Q. Now we can see in this question it is given that 50% of power is used up in heating the machine itself. Clear? So 50% of power is utilized in heating machine. Then what will happen? Clear? 50% of its power is used up in heating the machine. Okay. It means now we can see total energy that is available. Clear? So total energy this is available is 50% of total energy provided by this machine. Clear? So from here we can see this is equal to 7.5 into 10 to the power 5 joule. Clear? Now it means we can say this 50% of energy it is provided to aluminum block. Clear? Now our objective in this question is to find total rise in temperature of block. Clear? It means I can see this Q available. Clear? Q available, this should be equal to mc delta T. Now keep in mind the conversion of units. Clear? This value is given 7.5 into 10 to the power 5 in joule mass. Actually value of specific heat of volume is given joule per gram per Kelvin. It means you have to convert this mass first into gram. Clear? Because it is given 8 kilogram. So we can write here this is 8000 gram multiply, we can say 0.91 multiply what about delta T. Clear? What about delta T? So this is our objective. Yes or no? This is our objective. So from here you can say delta T, this is given by 7.5 into 10 to the power 5 divided by 8 into 10 to the power 3 into, I can say let's suppose this is 0.9 only. Clear? So from here we can write this is equal to 100. This point and point this is cancelled out. This is 3. We can say this is 25. Clear? So from here you can say delta T, this value is given 25 into 100 and this is divided by 3 into 8. Clear? So from here we can say this is equal to what? Near about 3. Clear? And this one is cancelled out. So I can say near about this value we are getting, that is 100 degree Celsius, or you can say the total rise in temperature is we will find near about 100 degree Celsius, or you can also say this is 100 Kelvin. Why? Because 1 degree Celsius is equal to 1 Kelvin if you find difference in the Celsius scale and the Kelvin scale. Clear? So this is all about this question. Now student, we are going to discuss this question number 11.13. Clear? In this question it is given to you a copper block of mass 2.5 kilogram is heated in a furnace to a temperature of 500 degree Celsius. Clear? So I can see mass of copper block, it is provided to you 2.5 kilogram. Clear? And temperature, or we can say temperature of that body, we can say it is given temperature of copper body, this is 500 degrees Celsius. Clear? Then it is placed on a large ice block. Clear? So let's suppose now we are placing this copper block on a large ice block. This is ice. Clear? And let's suppose this is copper ball. Clear? So our objective in this question is to find what is maximum amount of ice that can be melted. So directly you can say, if we assume that all the heat that is radiated by this copper block, we can say this is absorbed by ice only. Clear? At the time we can say directly, if we apply this concept, heat lost by copper block, this should be equal to heat gained by heat gained by ice. Clear? Heat gained by ice. So from here you can say heat lost by copper block. So what is heat lost by this copper block? Now it is given in this question specific heat of copper in joule per gram per Kelvin. It means you will write here first mc delta T, mu C for copper, mc delta T. Clear? And this should be equal to now heat gained by ice, because our objective is to find ice melted, amount of ice melted. Clear? So let's suppose this mass is m, and here we will write this is latent heat of fusion. Clear? Latent heat of fusion of water is also provided to you 335 joule per gram. It means definitely you will find this value of m in gram. Clear? So now I can put value 2.5, so I can say this is 2500 gram. Clear? Multiplied with specific heat of copper. Specific heat of copper, it is given 0.39 multiply. Clear? 2500 into 0.39 into delta T. Delta T means we can say initially this copper block is at a temperature 500 degrees Celsius. At ice means we can say this is 0 degrees Celsius. Clear? And this is equal to m times of 335. Clear? So from here we can say value of m, this is given by 2500 into 39 by 100 into 500, and it is divided by 335. Clear? From here we can say this one and this one is cancelled out. Clear? So from here you can say 12500 multiply 39 divided by 335. Clear to everyone? So now if we solve it, we will find our answer. If you cancel with 5, we can say 6 and this is 7, and we can say this is 2500. Clear? So from here you can say 39 multiply 2, this is what? 78. Okay, so how can we solve? If you multiply it with 4, you can say this is near about. Actually we can find near about answer. So 39 multiply 2 is 78. So we can say, let's suppose this is near about 1.8. Near about. Clear? So from here you can say this mass is given by 2500 divided by 1.8. Clear? So from here we can write like this. This is 0, 1. Clear? We have 7 left. So near about 1400 gram. Near about. Clear? Yes or no? So we can say this is amount of ice that can be melted by this copper block initially at temperature 500 degrees Celsius and finally coming to temperature at 0 degree Celsius. So almost 1.4 kilogram or 1400 gram of ice melted. Clear? So this is all about this question. Now dear student, we are going to discuss this question number 11.14, and in this question it is given to you in an experiment on the specific heat of a metal. A 0.20 kilogram block of the metal is at 150 degrees Celsius is dropped in a copper calorimeter having water equivalent 0.025 kilogram containing 150 centimeter cube of water at 27 degree Celsius. Fine. The final temperature is 40 degree Celsius. Now we have to find the specific heat capacity of this metal. Clear? Now let us try to understand this question. We have an experiment. Our objective in this question is to find specific heat of copper. So this is our objective. Clear? Mass of copper block or mass of block is given to you. This is 0.20 kilogram. Okay, fine. And initial temperature is 150 degrees Celsius, and whenever we place this into calorimeter, final temperature is 40 degrees Celsius. So what is value of delta T? I can say delta T is given by 150 minus 40, and this should be equal to 110 degree Celsius. Clear to everyone? So can we find here total heat lost by copper block? Yes. So heat lost. Clear? Heat lost, this is given by mc delta T. Clear? mc delta T. So what is value of m? M we can see, because keep in mind value of C. Actually all the things are given here. This is centimeter cube. So can we convert into gram? Yes. So from here we can see 0.2. So I am writing this is 20 gram. Clear? 200 gram. Clear? 0.20 kg equal to 200 gram. Specific heat in C. And what about delta T? Delta T is given 110. So we can say this is total heat lost by this copper block. Clear? 110. Now this heat that lost by this copper block, or we can say it is actually absorbed by water and calorimeter. Clear? So from here we can say heat gain. In heat gain we will write here mass of water plus mass of calorimeter, or we can say water equivalent. Clear? And it is multiplied with the specific heat of water and delta T. Clear? So from here you can see mass of water. Mass of water is present. It is given in this question. We have yes, specific heat is given containing 150 centimeter cube of water. Clear? Now we know density. Density is given by mass per unit volume. What is density of water in terms of centimeter? So from here we can say this is 1 gram per centimeter cube. Yes or no? Density of water is 1 gram per centimeter cube, and this is equal to mass divided by volume is given 150 centimeter cube. So from here you can say this mass of water is 150 gram. Clear? Mass of water is 150 gram. So from here we can say this is 150 plus. What about mass of calorimeter? It is given, this is 0.025 kilogram. It means I can say this is 25 gram only. Clear? Specific heat of water is given by 1 calorie per gram per degree Celsius. Clear? Always keep in mind Cw value we have 1 gram per degree Celsius. Clear? And actually this is what 1 calorie, because this is specific heat, so we can write like this. This is equal to 1 calorie per degree Celsius per we can say Cw. This is given by joule per gram. Yes, so we can say this is per gram. Clear? So value of specific heat of water in terms of CGS unit, or you can say in terms of calorie, we can say this is 1 calorie per gram per degree Celsius. So I am writing this value here. And what about delta T? Clear? So I am writing here delta T. Now we can say this is 175 into 1 and delta T. Delta T is what? Final temperature we have 40 degrees Celsius, but water is situated at 27 degrees Celsius. It means we can say this is equal to 40 minus 27. Clear? So from here we can write like this, 175 into 30. Clear? So this is heat gain. Clear? And this we will find in terms of calorie. Clear? Here we have all the terms. This is also calorie. It means we can write that heat lost is equal to heat gain. Clear? So now I can write like this, heat lost, this should be equal to heat gain. Clear? So in this question, what is value of heat lost? 200 into C into 110. So 200 into C into 100, and this should be equal to, clear? This is 110. Yes, and this should be equal to, we can say 175 into 13. Clear? So 175 into 13. Clear? From here can we calculate value of specific heat of this copper block? Yes. 175 into 13 divided by 200 into 110. From here we can say this is 7 and this is what? 8. If you cancel by 25. Clear? So from here you can say 7 multiply 13. So this is equal to 91 divided by, we can say 8 into 110. Clear? From here you can say 91 divided by 88 into 10 to the power minus 1. Clear? So from here you can say this is near about 1.1 into 10 to the power minus 1, and this value we will get in terms of calorie per gram per degree Celsius. Clear? So from here we can say value of C, this is given by 0.11, and this is calorie per gram per degree Celsius. Clear? So this is what? This is specific heat of a copper block. Clear? So now we can say actually one more thing is given. If heat losses to surrounding are not negligible, clear, then your answer is greater or smaller than the actual value of specific heat of metal. Now listen carefully. Whenever the total heat lost by this one, listen carefully, whenever total heat lost by this copper block, it will not equal to heat gained by this water, clear, or heat gained by calorimeter. So at that time how you will write? We can write like this, heat lost, this should be equal to, I can say heat gain plus some energy that is going to surrounding. Clear? Now you can say actually what I am doing here, actually we are actually if you know this value, listen carefully, if you know this value, actually we are doing here energy conservation, the total energy is conserved. Clear? And what about specific heat? Actually specific heat is the property of a material. Clear? So I can say the value of specific heat, it remains same, either if the some energy is going, if the some energy is going in the surrounding, then what will happen at that time, you can say that all heat that is lost by this block is not utilized to increase the temperature of this water up to 40 degrees Celsius. At that time what will happen, the temperature rises for water, it will rises below 40 degrees Celsius. Clear to everyone? But specific heat of copper block, that remains same because it is property of a material. Clear? So this is all about this question. Now student, we are going to discuss this question number 11.15, and in this question it is given to you, given below are observations on molar specific heat at room temperature of some common gases. Clear? Gases are given to you: hydrogen, nitrogen, oxygen, nitric oxide, carbon monoxide and chlorine. Clear? And their molar specific heat value is given at constant volume. Clear? Now it is given the measured molar specific heat of these gases are marked different from those for monoatomic gases. Okay, so molar specific heat of monoatomic gas is near about 2.92 calorie per mole per Kelvin. Now we have to explain this difference, why there is a difference in specific heat we find for these gases and monoatomic gases. Clear? Let us try to understand. Now dear student, you can see if we are talking about these gases, this is hydrogen, this is H2, we can say this is N2, this is what, oxygen, this is nitrous oxide. Clear? We can say this is carbon monoxide. Clear? This is chlorine. So from here you can say all gases, this is what, all gases are, we can say this is diatomic gases. Clear? Diatomic gases. So how can we define value of specific heat at constant volume? Actually this is defined in terms of degree of freedom. This is F by 2R, where F is what? F is degree of freedom. F is what? F is degree of freedom. So if we are talking about for monoatomic gas, for monoatomic gas F is equal to 3. Clear? And what about diatomic gas? Diatomic gases. For diatomic gases, this F value is near about, actually this value is 5 at normal temperature. And if we are actually also adding the vibrational mode of degree of freedom, at the time this degree of freedom becomes 7 at higher temperature. Clear? So from here you can see, if we write value of CV, this is given by F by 2R. Clear? So if I write value of CV for monoatomic gas, we can say CV, this should be equal to 3 by 2 times of R. Clear? What is value of R? We can say value of R is given, this is 8.31 joule per mole per Kelvin. Can we convert into calorie? Yes, we can divide with 4.2, and this will be near about 2. Clear? So from here you can say this is near about 3 calorie per mole per Kelvin, or you can say per degree Celsius. Clear? But what about diatomic gases? Clear? For diatomic gases, we can say value of specific heat at constant volume, this is given by 5 by 2 multiplied with R. Clear? So this is equal to 5 by 2 multiply R. R directly you can say this is 2 calorie per mole per Kelvin or per degree Celsius is the same. Clear? From here we can say for diatomic gases at normal temperature you will find this value near about 5 calorie per mole per Kelvin. Clear to you? Yes or no? And if you are also including vibrational degree of freedom, then its degree of freedom becomes 7. So at the time this is near about 7 calorie per mole per Kelvin. Now listen carefully. If you observe all these gases, you will find all these values near about 5. Clear? 1, 2, 3, 4, 5. All values are near about 5. Clear? But there is some variation in chlorine. Clear? The chlorine value you will find near about 6 point something. Why? Because at room temperature, there is some molecules of chlorine gas that is having vibrational in nature. Clear? So here we also include its vibrational degree of freedom. That's why you can see here we are getting this value near about 7, but at normal temperature you are getting this value near about 5, and for monoatomic this value is near about 3. Clear? So you can see that for a monoatomic gas this value we find near about 3. Clear? And for diatomic near about 5. And what about if you consider diatomic gas as well as you consider vibrational mode of degree of freedom, at the time this value is near about 7. Clear? So this is all about this question. Clear? Now student, we are going to discuss this question number 11.16. Clear? Again a very good question. In this question it is given to you a child running at a temperature of 101 degree Fahrenheit. Clear? In this question it is given a child running at a temperature of 101 degree Fahrenheit is given an antipyrine. That antipyrine is a medicine that lowers fever, okay, which causes an increase in rate of evaporation of sweat from his body. Fine. If the fever is brought down to 98 degree Fahrenheit in 20 minutes. Clear? So can we find here total decrease in temperature? Total decrease in temperature is given to you 101 minus we can say 98, and this should be equal to 3 degree Fahrenheit. Clear? Can we convert this temperature into degree Celsius? Yes. Actually we know if you find here this is 0 degree Celsius, this is 100 degree Celsius. Clear? This is what 32 degree Fahrenheit, this is 212 degree Fahrenheit if you consider temperature scale. At the time you can say this difference of 180 degree Fahrenheit, this should be equal to 100 degree Celsius. Clear? So from here can we write like this, 1 degree Celsius difference, it is equal to 1.8 degree Fahrenheit. Yes or no? So from here we can write like this, 1 degree Celsius difference is equal to 9 by 5 degree of Fahrenheit. Clear? So can we write like this, 1 degree Fahrenheit, this should be equal to 5 by 9 times of 1 degree Celsius. Clear? So can we convert this temperature into we can say degree Celsius? Yes or no? Yes or no? So from here we can say we can convert this Fahrenheit into degree Celsius. So for that one I can multiply here. So delta T, this is given by 3 degree F, or this is equal to 3 multiply 5 by 9, and this is degree Celsius. So we can say this is equal to 5 by 3, and we can say this is degree Celsius. Clear? So this is temperature difference, and this temperature is coming down in 20 minutes. So total time, this is temperature difference and time is given to you 29 minutes. Now in this question it is given what is the average rate of extra evaporation caused by drug. Clear? It means we have to find that evaporation rate. Clear? Now we have to assume that average we have to assume evaporation mechanism to be only way by which heat can be lost. Fine. The mass of the child is 30 kg. Okay, fine. The specific heat of human body is approximately same as the specific heat of water. Fine. And latent heat of evaporation of water at that temperature is about 580 calorie per gram. So all the information is given to you. Now how can we solve this question, and actually what is concept behind it? Clear? From here you can first find heat lost by child after taking medicine. Clear? And we can say that is equal to mc delta T. M is mass of that child, this is 30 kilogram. So let's suppose if we convert this into gram, we have to multiply it with 3. Specific heat of person, it is given in this question, specific heat of human body is approximately same as of water. So for water we know specific heat of water, this is given by 1 calorie per mole per degree Celsius. Yes or no? Or we can also say this can be write like this, 1 calorie per kilogram per degree Celsius. Yes or no? Because if we write Q equal to mc delta T, we can write like this. Clear? So from here if we write, because this is calorie, so we write this is gram. Clear? 1 calorie per gram per degree Celsius. So this is value we have 1. And what about temperature difference? Temperature difference is given in degree Celsius, this is 5 by 3. Now you can understand why we convert temperature from degree Fahrenheit to degree Celsius, because here we find this value in degree Celsius, clear? So now we can say this one and this one is cancelled out. So total amount of heat lost by human body, this is given. We can say 10 to the power 4 multiply 5, clear? And this value in calorie. So from here we can write like this, this is 50,000 calorie, clear? And this is what? This is heat lost. Heat lost is given by, this is 50,000 calorie, clear to everyone? Yes. So now this is 50,000 calorie. Now we can say this all heat lost by human body, that is given to sweat glands, clear? And after that there is a sweating is to be taking place. So can we write like this, this Q lost, it should be equal to mass, clear? Mass of evaporation multiplied with latent heat, and this latent heat is actually given, latent heat of evaporation, this is 580 calorie per gram, clear? So from here we can say this 50,000 equal to mass multiply 580, and we can say 580 what? This is calorie per gram, so this value again come in calorie. So from here you can find this value 5 m, this is 50,000 divided by 580, clear? So we can say this one and this one cancelled out, and if you solve it, you will find this answer near about 86.2 kilogram, clear? This is near about 86.2 kilogram, clear? So from here you can say this is mass of evaporation, and this is given by 86.2 kilogram, yes or no? 86.2 kilogram, clear? Kilogram or gram? Gram, because this value you are writing in terms of calorie, and this is also calorie per gram, clear? So here you will find this value in gram, clear? So this value we find 86.2 gram, clear? 86.2 gram. Now can we find rate of evaporation? Yes. Rate of evaporation means what? The mass of evaporation and divided by time, clear? So rate of evaporation, it is given by, this is equal to 86.2 divided by total time taken 20 minutes, so this is divided by 20. So from here we can say this is 8.62 divided by 2, and this is equal to 4.31, clear? This is equal to 4.31, and this value we can say this value is equal to what? We can say gram per minute, clear? Because this 20 is given to you in terms of minute, so we can say this is the correct answer of this question, clear? So what was our objective? Our objective in this question is to calculate average rate of extra evaporation caused by the drug, because normally according to we can say radiation laws, we can say any body is having temperature above 0 Kelvin always emits some radiation, but because that child is taking a drug, and that drug is responsible for extra evaporation, clear? So correct answer for this question we have, this is 4.31 gram per minute, clear to everyone? Now dear student, we are going to discuss this question number 11.17, clear? And in this question it is given to you a thermocol ice box. A thermocol ice box is a cheap and an efficient method for storing small quantity of cooked food in summer in particular. Fine. A cubical box of side 30 cm has a thickness of 5 cm, clear? So let's suppose I am drawing here a cubical box. So let's suppose this is just a front view, clear? Actually this is cubical box, clear? Just I am drawing like this. Yes. So let's suppose we have a cubical box. Listen carefully. I am directly writing cubical box, clear? So in this question it is given a cubical ice box of side 30 cm. So value of side it is given to you 30 cm, clear? Thickness value is given 5 cm, fine. And if 4 kg of ice, so total mass of ice is given 4 kg, clear? It is put in the box. Estimate the amount of ice remaining after 6 hours. So time is given in 6 hours, or we can say you can convert this hour into second. Yes, this is 3600 multiply 6 into seconds, clear? Now we can say the outside temperature is given 45 degrees Celsius, so you can find temperature difference, this is also 45, clear? Because 45 minus 0, ice is having temperature 0 degree Celsius. Coefficient of thermal conductivity is also given. So value of K we have 3, we can say 0.01. Value of K, it is also given 0.01 joule per second per meter per Kelvin. Okay, and latent heat of fusion, it is also provided 335 into 10 to the power 3 joule per kilogram. Clear to everyone? Now listen carefully. From here you can see, first let's suppose if I draw here this diagram, let's suppose you can assume this is a cube, this is cube, clear, this is cube. Now side of this cube is given to you already 30 centimeter, clear, and thickness means we can see this part from where this heat is actually coming from outside. Now you can say definitely heat will enter from each side of this cube, yes or no? Because ice is placed inside this cube, clear, and ice is at temperature 0 degree Celsius. Outside temperature is given 45 degree Celsius. It means definitely we have temperature difference. So some heat will enter from outside into this box, clear. So from here we can write like this. We can see first we calculate total area. So total area of this cube is given by 6 times of side square, clear. 6 multiply, what about side? Side is given 30 centimeter, yes or no? This is 30 centimeter. So 30 into 10 to the power minus 2 whole square. So from here we can say 6 into 30 into 30 into 10 to the power minus 4. This is in meter square. Clear? So from here we can say this is 9, and we can say 9 multiply 6, 54. Clear? So 54 into 10 to the power minus 2 meter square. So this is area. Clear? So A value equal to 54 into 10 to the power minus 2 meter square. Clear? So now from here can we find total heat that is entered from all the sides? Yes. So we can see this is given by one formula, Ka delta T by delta X, and this is multiplied with time T. Clear? From here we can write all values. So what is value of K? Value of K in this question, it is given to you 0.01 joule per second per meter per Kelvin. So 0.01. What about area? Total surface area 54 into 10 to the power minus 2. And what about temperature difference? Now you can say here we have 45 degree outside temperature, inside temperature we have 0 degree Celsius. So from here we can say this is 45 minus 0 multiplied. What about total time? Total time is given in this question. Yes, this is 6 hour. 6 hour means 6 into 3600. 6 into 3600, and it is divided by, I can say, total thickness. Thickness we have this one. This is known as thickness because heat is entering from this side. Clear? So we can say thickness is given 5 centimeter. So 5 into 10 to the power minus 2. From here you can say this one and this one cancelled out. This one and these two 0 is cancelled out. Clear? So now we have left 54 into 45 multiply 6 multiply 36 divided by 5. So from here we can say this is 9. Clear? This is 9. So value of Q, this is given by 54 multiply 9 multiply 6 multiply 36. Clear? So from here if you multiply, then we can say this is equal to what? 54 into 54 into 36. Clear? Now how can we multiply 54? We can say directly 4 multiply 4, this is 16. Then this is what? 20 plus 20, this is 40. Divide by, we can say this is 25. Clear? So 6, 1, we can say 9, and this is 2916. 2916. Clear? So this is 2916 multiply 36. Now we will multiply it with 36. Clear? So we can say this is 36, this one is 3, 9, we can say 9, 6, this is what? 54. So 54, we have 5, 12, and 12, 5, 17, multiply. Clear? From here we can say this is what? 18, we have 1, so this is 4, we can say 27, we have 2 left, so we can say that is 8. 6, I can say 9, 8, 70, we have 1, 5, 4, 9, clear, and we can say 7, 7, 14, again we have 1, so this is, we can say total value we are getting 104,976, and this value in terms of joule. Clear? So this is the total amount of heat that is entering from outside from all the surface, and this heat is actually utilized 104976. This heat is utilized to melt ice and latent heat. Now latent heat value is given 335 into 10 to the power 3. 335 into 10 to the power 3 in joule per kilogram. Clear? So now can we calculate value of m of ice? Yes. So we can calculate like this. Mass of ice, this is given to you. Clear? 104976 divided by, now we can say 10 to the power 3, so this is 1. Clear? And this is 335. Clear? So near about you can say 105 divided by 335. Clear? So if you solve it, you will find this is 0.313 kilogram. Clear? So this is what? This is mass of ice that is melted. Clear? After 6 hours. Clear? So what is the total amount of ice remaining? Clear? Now what is total amount of ice remaining? Clear? So total amount of ice remaining we can calculate like this. We can say total amount of ice remaining. Clear? So we can say mass of ice, this is remaining. Clear? Mass of ice remaining, and that is given by 4 minus and this is 0.313. Clear? So from here we can say this is equal to what? 9, and we can say this is what? 9, this is 8. Clear? Again we can say this is 6, and we can say 3. Clear? So 3.689 kilogram. Clear to everyone? Yes or no? Actually this is 7. This is my mistake. This is 7. Clear? So we can say 7, 7, 3 we have 10. Clear? We have 1. So 2, 10. Again we have 1. Correct. Clear? So 3.687 kilogram. This is a mass of ice. This is remaining. Clear? So this is all about this question. Now student, we are going to discuss this question number 11.18. Clear? In this question it is given to you, a brass boiler has a base area of 0.15 meter square and thickness 1 centimeter. Clear? So in this question it is given area, this is 0.15 meter square. Clear? And what about thickness? Thickness is given, this is 1 centimeter. Clear? So let's suppose I am drawing, let's suppose you can assume this is a boiler, for example boiler, and this is made up of brass. Clear? We can say, let's suppose this is a gas stove and from here the flame is coming. Clear? And let's suppose we have water. So because this is a brass boiler, so function of a boiler is to convert this water into steam. Yes or no? So actually whatever heat that we are providing from outside, it is utilizing to convert water into steam. Clear? So from here we can say a brass boiler has a base area. Base area is given 0.15 meter square, 0.15 meter square, and thickness is given to you 1 centimeter. Okay. It boils water at the rate of 6 kilogram per minute. It boils water at the rate of 6 kilogram per minute. Clear? So now we can say, if you are talking about time is given, this is 1 minute, or we can say that is equal to 60 seconds. Clear? 60 seconds. You can assume this thickness is to be x. Clear? So that you will not confuse with time. Clear? So x is given 1 centimeter. Actually this thickness is what? This is thickness. This thickness is 1 centimeter. Clear? Now it is also given mass of water. Mass of water, this is equal to 6 kilogram, and we can say this is equal to 6000 gram. Clear? Now how can we solve this question and what is our objective? Estimate the temperature of part of a flame in contact with the boiler. Clear? So now we can say heat that is transferred from outside, or we can say if this is a conductor, at the time can we find the rate of heat transfer? Yes or no? So we can write like this, this is Ka delta T divided by delta X multiplied with time T. Clear? So now we can say K, value of K, it is thermal conductivity value given, yes, 109. What about area? Area is given 0.15. Clear? And multiplied with delta T. Delta T means temperature difference. Temperature difference is given, yes or no? Temperature difference, yes. Temperature difference, we can say, let's suppose temperature of flame is T1. Clear? And because water is boiling, so water is boils always at 100 degrees Celsius if atmospheric condition is not changing. Clear? At the time, divide by thickness, it is 10 to the power minus 2 meter, and multiplied with, I can say time is given to you 60 seconds. Clear? So from here we can write like this, 109 into we can say 50 by 100 into T1 minus 100, clear, multiplied with 10, we can say 100 into 60. Clear? From here we can see this one, or we can say 100 and 100 cancelled out directly. Clear? So dear student, now we can say this value of Q we have 109 into 15 into T1 minus 100, clear, and multiplied with 60, and this should be equal to, now we can say this heat is utilized to convert this water into steam. So we can say mass is given to you 6 kilogram, so we can say 6 into 2256 into 10 to the power 3. Clear? So from here you can see this is equal to what? Let's suppose I am taking, if you multiplied it, we can say 15 9, we can say 135, we have 5, we have 3, and this is 15. Clear? So 15 9 135, we have 13, so we can say 15, this is 8, clear, and we have 2, so 15 to 17, 1785, clear. So this is 1785, clear. Or you can also say, you can do some calculation, this is 2, this is 5, clear. So 5, so we can say this is 45, we have 4, and this is 545, clear, and this is T1 minus 100 and 10, and this one is cancelled out, clear, multiplied with 6, clear, and this should be equal to 2 into 2256 into 100, clear. Now if you solve it, clear, if you solve it, you can say this is 45, if you multiply it with 4, this is 180, and 180 near about, you can say near about, I am saying this is 4, clear. We can say this value we have 3, so from here you can say 3T1 minus 300, this should be equal to 400, yes or no, clear. So from here you can find this value in terms of degree Celsius, yes or no, in terms of degree Kelvin. So overall if you calculate, you will find this value 3T1 equal to 700. So value of T1, this is given by 700 divided by 3, clear, and this should be equal to, we can say 3 to 6, we have 3, and we can say this is degree Celsius, clear. So this is the temperature of flame that we are getting, that is required to heat this water or to convert this water into steam in brass boiler, clear. So this is all about this question. Now dear student, we are going to discuss this question number 11.19, clear. In this question it is given to you, explain why. Number 1, a body with large reflectivity is a poor emitter, clear. Now listen carefully. If we know that if we have any body and temperature of that body is above 0 Kelvin, that body emits some radiation, clear. So now whenever we are talking about a body with large reflectivity means directly we can say that body is having poor absorptivity. Whenever a body is having poor absorptivity means its absorptance value is very small, clear. At that time if we apply Kirchhoff's law of heat radiation, at that time you can say if absorptivity is less, then emittivity or emittance is also less, clear. So we can say according to Kirchhoff's law of heat radiation, a body with poor emitter is a body with poor absorber is also a poor emitter, clear. So this is what, that if we have large reflectivity, we have poor emittivity, clear. Second, a brass tumbler, it feels much colder than a wooden tray on a chilly day, clear. Now let's suppose here I place any object, let's suppose I place a brass tumbler, clear, and we can say we have a wooden tray. Let's suppose we have winter's day, and let's suppose when we touch this brass tumbler, at the time what happened, because brass is a good conductor of heat, at the time some heat will flow from my body to that brass, clear, and at the time because I am losing some energy, so that I will feel cold, clear. But in the case of wood, we can say wood is a poor conductor, or we can say wood is actually an insulator, clear. So we can say a very less amount of heat, or we can say no heat will flow to the wood. So at the time you can say that I will feel no cold, no hot, because I will feel no sense. Clear? So from here you can see that a brass tumbler feels much colder than a wooden tray. Clear? Now, third one. If I am talking about C part, an optical pyrometer for measuring high temperature calibrated for an ideal black body radiation gives too low a value for temperature of a red hot iron piece in open. Now listen carefully. Actually, let's suppose we have an iron piece. Let's suppose this is iron piece having temperature T. It's Stephen Boltzmann constant we know. Let's suppose sigma, and let's suppose when we place this object in the furnace. Clear? So we can say at this furnace we have the same temperature T. So total amount of radiation that is emitted by this body, it is given by sigma T to the power 4 if we are considering unit area. Clear? And this value is actually read by optical pyrometer. Optical pyrometer is an instrument which is used to measure the heat radiation. Clear? But what about if I place this hot iron at the room, or we can say in the open atmosphere? At the time you will find this value of heat radiation, this is given by T to the power 4 minus T naught to the power 4. Clear? At that time we can say directly you can observe this E dash value is less than E. Clear? So when E dash value is less than E, it means I can say less amount of radiation emitted. Less amount of radiation emitted. So we can say optical pyrometer, it will provide you a low value. Clear? You can see because atmosphere is also having a temperature, so at the time some heat is to be given to that body also, and that body is also losing some energy. So at the time I can say this is value of net heat radiation. Clear? So that's why optical pyrometer provides you a low value. Clear? Done. Now if I talk about part number D, the earth without its atmosphere would be inhospitably cold. Exactly true. Why? Because we know that some radiation that is coming from sun, our earth is actually emitting some, or itself emitting some radiation. Actually our atmosphere that absorb that heat and again reflect that heat to our earth. So that's why we can say that our atmosphere temperature, it remains maintained constant. Clear? Or at the time actually that is also required for the survival of human beings and other living beings. Clear? But what will happen if we have no atmosphere? At that time you can say there is no greenhouse effect, or we can say the radiation emitted by earth, it will go out of the earth. Clear? And at that time you can say that we will feel cold. Clear? So this is all about this question. If we are talking about part number E, part number E is given heating system based on circulation of steam are more efficient in warming a building than based on circulation of water. Exactly true. Because if I am talking about latent heat of fusion, actually we have two terms. Number one term we have latent heat of fusion. Latent heat of fusion is the amount of heat required to melt ice into water. Clear? And this is near about, definitely you know this is 80 calorie per gram. But what about steam? If I talk about latent heat of vaporization, if I am talking about latent heat of vaporization, its value is given by 540 calorie per gram. So from here you can observe, for if you want to convert 1 gram of water into steam, then definitely we can see the much amount of heat that is given. Yes or no? It means we can see if we are circulating water, or let's suppose if I am circulating steam, so more amount of heat that can be extracted from the steam. That's why we can say that heating system based on circulation of steam are more efficient in warming a building. Clear? Actually you have to take care at most whenever you are dealing with steam, because it is very dangerous, because pressure created will be more and more amount of heat is generated. Clear? So this is all about this question. Clear? Now dear student, we are going to discuss this question, and this question is related to Newton's law of cooling. Clear? This is a question number 11.20, and in this question it is given a body cools from 80 degrees Celsius to 50 degrees Celsius in 5 minutes. Okay, fine. Calculate the time it takes to cool from 60 degrees Celsius to 30 degrees Celsius, and the temperature of surrounding is given to you 20 degrees Celsius. Clear? So from here you can see actually what is Newton's law of cooling. Newton's law of cooling says the rate of heat loss by a body it is directly proportional to temperature difference between body and the surrounding, provided that that difference is small. Clear? So let us try to understand. Let's suppose we have this body. Clear? Mass of this body is given to you m, specific heat is C, and let's suppose temperature is T. Clear? Let's suppose we are having surrounding temperature T naught. At that time you can say minus mc dt by dt. Clear? And this is what? Rate of heat loss. Clear? This should be equal to, or we can say this should be equal to Ka delta T by delta X. Clear? Yes or no? So actually if you solve this expression, clear? If you solve this expression, you will find this one m c, this is what? T1 minus T2 divide by time t. This should be equal to, we can say Ka, clear? Ka, and we can say here we write Ka delta T by we can say this is equal to what? Actually, always keep in mind the concept of Newton's law of cooling. Newton's law of cooling is the rate of heat loss. This should be equal to directly. This should be proportional to. This should be proportional to temperature of that body and difference of temperature of that body and temperature of surrounding. Clear? So from here you can say mc T1 minus T2 divide by T. It should be equal to K. And what about T? T is average temperature, and we can say this is T1 plus T2 divided by 2 minus T naught. Clear? T1 plus T2 divided by 2 minus T naught. Clear? So from here you can say, according to given question, we can say mass of body is m. Clear? Specific heat, let's suppose this is C. Initial temperature is given 80 to 50. So 80 minus 50 divided by, what about time? Time is given 5 minutes, 5 into 60, it is converted into second. K is constant. Clear? K is what? K is constant. K is constant. Now we will take it average value. So average value we have 80 plus 50 divided by 2 minus we can say surrounding temperature. Surrounding temperature given, yes, this is 20 degree Celsius. So this is 20. Clear? So from here you can write like this, mc, this is given by 30 divided by, we can say this is 300, and this should be equal to K. 80 plus 50, this is equal to what? 130. 65 minus 20. Clear? So from here you can say we are getting one equation we have mc, and this is equal to what? We can say 30 by 300, and this should be equal to, we can say this is 45K. Clear? 45K, equation number 1. Clear? Similarly, if you apply same for 60 to 30 degrees Celsius, clear? We can write like this, mc, this is what? 60 minus 30 divided by, let's suppose time t in second is t. Clear? And this should be equal to something constant. Now what is average value of 60 and 30? So 60 plus 30 divided by 2 minus surrounding temperature is given, this is 20. Clear? Yes or no? Surrounding temperature is 20. So from here we can say this is mc, and we can say this is 30 divided by t. Clear? 30 divided by k, and this is equal to K. Now 60 plus 30, this is what? 90. I can say this is 45 minus 20. Yes or no? So from here you can see this mc 30 by t, this should be equal to K times of 25, and this is, let's suppose, equation number 2. Clear? Now you can say our objective in this question is to find this value of t. So one equation divided by equation number 2. Clear? In one equation it is given mc, so mc and mc cancelled out. Directly we can say this is 30 by 300. Clear? This is 30 by 300, and this should be divided by 30 by t. Clear? And this should be, clear? Now you can say k and k cancel out, 45 divided by 25. Clear? From here you can say 30 and 30 cancelled out, so we are getting 3 by t by 300. T by 300, and this should be equal to 9 by 5. Clear? From here we can say this is 60, so we are getting this time t, this is equal to 540 seconds. Clear? And we can convert this into minutes. Yes, you can divide with 60, so directly you can say in 9 minutes. Clear? So from here you can say that in 9 minutes this body cools from 60 degrees Celsius to 30 degrees Celsius. Clear to everyone? So this is all about this question. Now dear student, we are going to discuss this question number 11.21. And in this question it is given to you, answer the following question based on the PT phase diagram of carbon dioxide. Clear? So PT phase diagram of carbon dioxide is given to you here, and you have to provide answer of these following questions. Clear? Now part number A. At what temperature and pressure can solid, liquid and vapor phase of carbon dioxide coexist in equilibrium? Clear? Now you can see, if you concentrate on this diagram, solid, liquid and vapor all phase coexist at point O. Yes or no? Clear? At this point you can see solid phase, liquid phase and vapor all are existing simultaneously. So this is known as, we can see at what temperature and pressure. So directly answer of this question we have temperature. Temperature we can say that is minus 56.6 degrees Celsius. Clear? And what about pressure? Pressure is given to you 5.11 atm. Clear to you? Clear? Yes. Now we will going to discuss part number B. What is the effect of decrease of pressure on fusion and the boiling point of CO2? Now you can say, actually this line OA, this line represent fusion curve. Clear? And this represent boiling. Why? Because you can see this OA line separates solid and liquid, so this is related to fusion, and this OC line separates liquid and vapor, so it is related to boiling. Clear? Now you can say, if we are decreasing pressure, let's suppose if we are talking about this point and this point. Clear? Now if you are decreasing pressure, at the same time you can see temperature is also decreasing. Clear? So in this case I can say, if I decrease, clear, what is question? What is effect of decrease in pressure? Clear? So if we are decreasing pressure, clear, at the time decreasing pressure at the time fusion and boiling point decreases. Clear? You can say, actually what is meaning of boiling point and fusion point? We can say initially we have 31 degrees Celsius, after that we have 20 degrees Celsius, because this is decreasing. Clear? Here you can say initially you have fusion. Clear? We can say that is melting point, this one. Clear? And after that, if you are decreasing pressure, this value is also decreases. Clear? So directly we know decreasing pressure, fusion and boiling point decreases. Clear? Decrease. Now if we are talking about part number C, in part number C it is given, what are the critical temperature and pressure for carbon dioxide and what is their significance? Now if you observe this graph, you can say point C represent the point that is related to critical temperature. Critical temperature means we can say corresponding to this critical temperature we have pressure, this is 73 atm. Clear? And what about temperature? Temperature is 31.1 degrees Celsius. Now what is significance of this critical temperature? Significance of this critical temperature is that after this temperature you cannot liquefy carbon dioxide gas. Clear? However, large pressure you are applying, but that carbon dioxide always remain in a vapor phase. Clear to everyone? So this is the meaning of critical temperature. Clear? Now we are going to discuss part number D. Is CO2 solid, liquid or gas at minus 70 degrees Celsius under 1 atm? Clear? Now listen carefully. Where is minus 70? Let's suppose I am assuming minus 70 is here. Let's suppose here. Clear? And under 1 atm. So you can say that intersecting point we are finding in vapor region. Clear? So in vapor region I can say for part number D, I am writing this A point. We can say in this case CO2 rise in a vapor region. Clear? In this case, in this particular case, this CO2 lies in vapor region. Clear? What about part number B? Minus 60 degrees Celsius under 10 atm. Clear? So minus 60 means somewhat lie between this and minus under 10 atm. Clear? It means, let's suppose at this point this is minus 60 and let's suppose here we have 10 atm. So that point is somewhat lie in this location. It means we can say at this time CO2 lies in the form of solid. Clear? So you can say it lies in solid region. clear. And what about part number C, 15 degrees Celsius under 56 atm, clear. 15 degrees Celsius, so let's suppose near about this, and under 56 atm means that point is lies near about this one, clear. It means we can say at this situation this CO2 gas is lies in a liquid region or in a liquid form, clear. So you can say this is liquid, clear. So let's if you want to find the CO2 is a solid, liquid and gas, always according to given condition draw some parallel or vertical lines and try to find intersecting point, and that intersecting point is lie in a solid, liquid or vapor region you have to find. Clear to everyone? So this is all about this question. Now dear student, we are going to discuss question number 11.22. Again this question is related to PT diagram of carbon dioxide. So now concentrate. Answer the following question based on PT phase diagram of CO2. Clear? Now part number A. CO2 at 1 atmospheric pressure and temperature minus 60 degrees Celsius, clear. So where is 1 atmospheric pressure? You can see this is 1 atmospheric pressure and at minus 60 degrees Celsius. So we can say if you extend this one, and definitely this minus 60 degrees Celsius you will find at this location. So you are finding this intersecting point here, clear. Now in this question it is given CO2 at 1 atmospheric pressure and temperature minus 60 degrees Celsius is compressed isothermally, clear. Does it go through a liquid phase, clear. So from here you can say if I compressed isothermally means we can say we are increasing pressure and temperature is not changing. So definitely we can say this will move like this, clear, vertically in upward direction like this. So from here you can say if you are talking about part number A, in part number A this is directly converting into vapor to solid. This is directly converting vapor to solid without going in a liquid phase, clear. So what is this question? Does it go through liquid phase? No, clear. Here we have answered no, it does not going through a liquid phase. Clear to everyone? Yes. Now next one. Next part is given to you. What happens when CO2 at 4 atmospheric pressure is cooled from room temperature at constant pressure? Okay. So what about 4 atmospheric pressure? So near about this one, and at room temperature means near about 27 degrees Celsius. So this line is almost this one, clear, this one. So from here this is my intersecting point. Now actually I am decreasing temperature. I am decreasing temperature at constant pressure means now I am going like this. I am going in this direction, clear. At that time you can see directly phase of CO2 is changing from vapor to solid without going in liquid, clear. So I can see for part number B this is vapor to or yes, actually the temperature is given, pressure, yes, 4 atmospheric pressure, yes. So 4 atmospheric pressure I can say again vapor to solid, clear, vapor to solid, clear to everyone. So it is cooled, so definitely it is directly converting into vapor to solid, clear. Next one. Now if we talk about part number C, describe qualitatively the change in a given mass of a solid CO2 already given at 10 atmospheric pressure and at a temperature of minus 65 degrees Celsius, clear. So 10 atmospheric pressure is somewhat here, clear, and minus 65, so we are taking this one. So let's suppose this is the initial position, clear. Now it is given in this question that we have to find it is heated up to room temperature at a constant pressure. So room temperature you assumed at this point, clear. So now this is going like this, clear. At that time you can see initially CO2 is at in a solid state, after that it is going in a liquid state, and after that this is going in a vapor phase, clear. So here you will find all we can say phases, solid to liquid, and then liquid to vapor, clear to everyone? Yes. Now if I am talking about part number D, clear. So in part number D it is given CO2 is heated to a temperature 70 degrees Celsius. CO2 is heated to a temperature 70 degrees Celsius and compressed isothermally, okay. CO2 is heated to a temperature 70 degrees Celsius and compressed isothermally. Now listen carefully. now you know that critical temperature of CO2 is 31.1 degrees Celsius. After that, if you are heating beyond that temperature, that CO2 will actually will never go in a liquid phase, and it always try to remain in vapor phase. Clear? So now we can see what is this question. CO2 is heated to a temperature 70 degrees Celsius and compressed isothermally. What changes in its property do you expect? So I can see for part number D, no change in any phase. No change in any phase, because this temperature is above the critical temperature. Clear? So this is all about this question. Clear? So dear student, this is all about all NCERT and exercise solutions of chapter number 11, thermal properties of matter of class 11. So hope you enjoyed this session, as well as you will find here detailed video solution. So definitely it will be very useful for you for your upcoming examination. Clear? So this is all about this session. Thank you so much.